I'll go ahead and introduce the second speaker for this session. So the authors of the paper are Lidia Al-Zogbi, Anirudh Topiwala, Thorsten Flater, and Alex Krieger. And our speaker today is Lidia. Okay. Lidia Al-Zogbi. And the title of the talk is Deep Learning Techniques for Abdominal Skin and Wound Segmentation. Presenter mode. Yeah.
All right. Good morning, everyone. My name is Lidia, and I work with Dr. Axel Krieger, and I'm going to present to you the deep learning techniques that we use for abdominal skin and wound segmentation. So basically, why do we need skin segmentation? It's playing an important role in a large variety of biomedical applications. You want to monitor wounds, you want to segment them out, you want to track skin conditions of patients, you want to extract physiological insights from these images. There's a lot of reasons why people might be interested in skin segmentation, even besides biomedical applications, like for face tracking and gesture tracking. However, most of contemporary research is primarily based on facial and hand skin data set. So you can see that one data set has a few hands and faces in it, but it's still not very generalizable. The second one, SFA, is just for faces, and then you have just hand data sets for gesture recognition. So abdominal skin has basically different RGB, HSV, and YCBCR color pixel distributions. If you can look at the graph that I'm showing over here, we can see that we have 30 images from ECU and HDR datasets, which, if you can look over here, they are facial and hand datasets. And then we have abdominal skin, and you can clearly see that we're adding extra information with the abdominal dataset. Unfortunately, no abdominal skin segmentation technique evaluation has been present simply because the dataset is not existent. Because it can encompass supplementary information on skin features, the need for it is clearly obvious. It doesn't just improve segmentation on abdomens themselves, it can improve segmentation on other skin regions. Now, why would you consider segmentation on abdomens? So it can basically enable autonomous robotic diagnostics. So if you can look over here in the picture, it's a robot that's being developed in the medical robotics lab, where we have an ultrasound probe which is supposed to perform autonomous ultrasound scans. So what will the camera visualize is basically an image like this. This is just an ideal scenario. It's not going to be such a well-defined abdomen in real life. And effectively, you want to be able to segment this out to find the scannable skin regions. So priorly before that, skin segmentation has been done using traditional techniques. Now the problem with skin segmentation is that it's hard to do because there's a lot of variations from patient to patient. There's external factors coming into play, like illumination, background, image quality. More traditional techniques are not the best option because they rely on predefined models, which are very, very dependent to the training data. And some people, to compensate for that, have tried to develop statistical methods, but again, they're going to mitigate the fact that we are not defining exact values, but they're still going to be dependent on the training data. With the recent advances in machine learning, researchers have successfully experimented with skin segmentation using deep learning techniques, basically. However, because we don't have, again, an abdominal data set, no technique has been evaluated for that. So basically, we are trying to mitigate these problems with our current research work. So the methodology that I'm going to follow, and which is basically the outline of the presentation, I'm going to talk how we developed an abdominal data set, we hand-selected them and segmented them. I'm going to talk about a traditional technique used for skin segmentation. Then I'm going to propose a machine learning technique to improve that technique, to improve it. And then we're going to adapt deep learning techniques for skin segmentation. One of them is called UNet, the second one is MassCar CNN. And finally, we're going to demonstrate how the addition of that abdominal data set not just improves the segmentation of abdomens, but it also improves the segmentation on other skin regions. Compiling an abdominal data set. So basically, if you can look, these images are similar to what I've showed you as seen from the robot. So we have basically collected 1,400 images from Google, 227 by 227 pixels. And we split it into two halves. So basically, half of the images are going to be for lighter skin people, the other half for darker skin people, because we want to prevent any biases in both training and testing. So skin pixels form 66% of the entire pixel data, which means that we don't have an unbalanced data set. And we have a mean of 54.4% and a standard deviation of 15%, which basically tells you that it's not like we have half of the pictures having 2 skin pixels and then the other half of the pictures having 99% of skin pixels. So data is more or less balanced. And also you can see over here that the variation in the background is, it encompasses also the values for pixels on the actual skin. So basically this will encourage the algorithm not just to take into account texture and color, but to take into account contextual information. So one traditional technique, which is thresholding, it puts boundaries on skin pixel values in predetermined color spaces. RGB is not recommended to be used as a standalone color space, so we use 2 other color spaces. The decision boundaries are represented in the equations. You don't really have to understand exactly what's happening here. The point is that all of the values that you see, these are values that we had to manually determine them. So we had our data set and we just manually determined what better fits the data set, which is a very tedious problem. You don't want to keep on doing that. You don't guarantee reaching the proper values. I think there are like 14 values which you would want to manually optimize on. So what we did is that we created a fully connected features network to create a virtual decision boundary replicating these equations. So basically we have the 7 hidden layers. The information on the network is available in the slides. The interesting part is that we use 9 neurons for input. So it takes RGB, HSV, YCBCR values. These are considered as our features. So this is what the network takes as input, and then it processes all the information through hidden layers, dropout layers, and at the end it gives you an output, a class which is 1 or 0, 1 for skin and 0 for non-skin. And then we decided to try a deep learning technique called UNet. The architecture is, I think it's a very good architecture. It was primarily designed for segmenting grayscale images. It's a very popular technique in biomedical applications, and we had to modify the architecture so that it can take an input of 3D basically matrix, because we have colored images and not grayscale images. And basically we're using value activation functions. We have a total of 23 convolution layers and a bunch of different parameters which you can read out if you want. And then we have mask RCNN, which we tried to use because it forms a very different learning algorithm from the previous techniques. Basically, a mask RCNN is an extension of faster RCNNs, and the way it works is that ROI is a region of interest. It proposes different boxes, which are called the regions of interest, and then the faster RCNN would basically classify these boxes pertaining to different classes. So in this case, they add an extra convolution layer to perform the segmentation mask. So the segmentation mask is performed through the convolution procedure. And we use Matterplots implementation. What I want you to know is that all of the parameters that I'm mentioning in all of the networks, the learning rate and the weights and the optimization algorithms, SGD and Adam, we all determined them using a grid search. So we ran multiple of these parameters so that we can determine the optimal values. These are the implementation details. So we used four GPU memory cards. The total training times were 6, 5.2, and 13.2 hours for each of the fully connected UNet and mask RCNN. The methods were evaluated using a 10-fold cross-validation approach, which basically says that after we ran each network with the optimal parameters 10 different times, and then we averaged out the results for that. And that will prevent us from just saying that, okay, we got good results just based on luck. Because everything is stochastic, and even if you run the network with this, if you don't fix your seed, you will keep on getting new random numbers, and we don't want our good results to be based on just the randomness of the algorithm. So we use the following performance metrics because accuracy alone is not going to be enough, and recall and F measure, they give a lot of information on what's outputted, and besides that, it's going to give us the chance to compare our results to other people's results. I'm showing the data sets that we've used for training, for validation, and for testing. So we did 2 runs, basically. One, we wanted to find what were the accuracies on the abdominal testing, and then we wanted to find how much will the abdominal data set improve accuracies on the other non-abdominal skins. Because, right, we want to have a holistic skin segmentation. We don't want to just specifically segment out abdomens and nothing else. So these are some of the results. I'm highlighting them to make it much easier to read and not get confused because it's a lot. So basically, UNet achieved the best performance. It gives us high precision, high recall, And the network is able to retrieve a lot of the pixels. Even if you can look at the box plot, you can see that it gives pretty good results, very condensed results. Like 50% of the data is somewhere between 93 and 97%, which is a very good result. These are on our abdominal dataset. So letter A stands for the abdomen. And mass-Parsennen did not perform particularly well because I think it's because of its region proposal algorithm. It doesn't really adapt well, just the way it works. The variability of skin areas, so we have arms, and then we have fingers, and then we have abdomens, a lot of variation in the shape and the area covered in the images, and mass-Parsennen does not seem to deal well with these kind of problems. And then the features network did improve on the thresholding. For medical applications, these are not good enough results, but we were just showing that, yeah, it's probably easier to find the optimal values using a neural network than manually sitting and just finding what best suits this application. And we're also able to show that we have an improved performance on other data sets after adding the abdominal data set into the training. So P refers to Pratipan, which is a data set commonly used, and then the last two rows of the table, these are other people's results. And yes, you can see these are the most recent results. We do have better accuracies than what has been reported in the state-of-the-art techniques. So, and we have the same thing for the ECU data set where we obtain very, very good accuracies. We get the best accuracy so far. So these are some visual results that we are showing. So we can see some mask for the abdominal data set using the tested methods. We see some problems where we don't get very good accuracies, like with orange color. These are some stuff that need to be mitigated. And we're also showing, for example, on the right side, how the abdominal skin data set is improving the segmentation, not just on abdomens, but also on other data sets. So the last column shows the results without the abdominal data set. And then finally, there's something to look forward to, which is the wound segmentation using the network. So we would want to invert the skin masks and find wound segmentation results. And by doing that, we are showing some preliminary results which we were able to obtain based on just the unit model that we have trained based on just the skin segmentation. So we haven't added any wound, we don't have any bloody images in our training data set, and we were still able to obtain a good starting results, basically. So in conclusion, UNET is a very good performing network. We had the best average and median accuracies. Adding the abdominal data set improved the segmentation for our abdomens, and it also improved the segmentation for other data sets. So yes, it can be used and it can be pretty useful for other applications. We have a promising wound segmentation that can be achieved by inverting the skin segmentation mask, but that still has to be further analyzed. And then we were showing that successful integration of machine learning into biomedical robotics opens up the possibilities for more accurate, reliable, and intelligent systems. These are my references, and thank you. And if you have any questions, I'll be happy to take them.
I'd also like to ask the third speaker to come up and set up.
What are the largest corner cases or error cases for this sort of classification algorithm?
Over here, you mean like the largest error, the smallest accuracy?
Like, what are some types of images that cause the most problems with these sorts of?
Basically, if you can. Oops, sorry about that. Majorly orange-colored stuff, basically based on colors. And orange color creates a lot of problems. So other like skin color in the background did not create problems. Some occlusions do create a bit of problems. If you have like objects occluding, that also creates a bit of problems. Yeah, these are the cases that don't perform particularly well.
Any more questions? Okay, back there.
You train on 1,400 images, which sounds relatively small. Would it be interesting to take face data? Would it be interesting to take face or hand data sets as an augmentation?
Yeah, I may not have explained it well, but I've trained on a whole bunch of other images. So if you look at the table over here, so these are the total images from every single data set that we have considered.
I see, I didn't get that.
So yeah, but 1,400 is not going anywhere. That's very little. Yeah, we took into account other training images. Yeah.
Thank you. Okay, let's thank the speaker again.